Ever wonder how one material, steel, can be so versatile? It can be soft enough to bend or hard enough to cut through rock? The secret isn't magic, it's metallurgy. And today, we're diving into two of its most important tools, phase diagrams and TTT curves. So what's a phase diagram? Imagine it's a recipe book for steel. On one axis, you have temperature, and on the other, the amount of carbon mixed with iron. This chart, specifically the iron-carbon diagram, tells us exactly what phase or state the steel is in at any given temperature and composition. Think of these phases like states of water, ice, liquid, and steam. For steel, we have different solid forms with unique properties. Let's look at the key players in this diagram. First, there's ferrite. This is the soft, ductile, magnetic phase of steel that exists at lower temperatures. It doesn't hold much carbon. Then we have austenite, the star of the show. Austenite only forms at high temperatures. It's non-magnetic, and it can dissolve a lot more carbon. This is the phase we start with for most heat treatments. Finally, there's cementite, or iron carbide. As its name suggests, it's hard and brittle, like cement. The balance between soft ferrite and hard cementite is what gives steel its strength. A crucial spot on this map is the eutectoid point. At exactly 727 degrees Celsius and 0.8% carbon, something special happens. Austenite transforms directly into a layered structure of ferrite and cementite, called pearlite. This point is the foundation for understanding how most common steels behave. Now, knowing the phases is one thing, but how do we control which ones we get? That's where the TTT curve comes in. TTT stands for time temperature transformation. While the phase diagram is a map of what's possible, the TTT curve is the GPS that tells you how to get there. It shows how long it takes for austenite to transform into other structures at a specific constant temperature. Let's break down the TTT curve. The chart has temperature on the vertical axis and time on the horizontal axis, usually on a logarithmic scale. You'll see these C-shaped curves, often called noses. If you cool your hot austenite down and hold it at a temperature high on the chart, above the nose you give the carbon atoms plenty of time to move around. They'll form alternating layers of ferrite and cementite, creating pearlite. The higher the temperature, the coarser and softer the pearlite. Now, what if we cool it a bit faster and hold it at a temperature just below the nose of the curve? Here, the atoms have less time to organize neatly. This creates a much finer, feather-like structure called bainite. Bainite is harder and stronger than pearlite, but still has decent toughness. But what if we want extreme hardness? This requires a very fast cool, a process known as quenching. If we cool the austenite so rapidly that we miss the nose of the TTT curve entirely, the carbon atoms get trapped inside the iron crystal structure. They don't have time to form ferrite or cementite. This new, highly stressed and distorted structure is called Martensite. It's incredibly hard and brittle, which is perfect for things like cutting tools. But it often needs to be tempered or slightly reheated to reduce that brittleness. So why does all this matter? It's the core of heat treatment. By understanding these diagrams, engineers can precisely design the cooling process for a piece of steel to achieve a specific set of properties. Do you need a tough and durable axle for a truck? You might aim for a Bainite structure. Need a super hard chisel? You'll quench to form Martensite and then temper it? Want a general-purpose steel with a good balance of properties? A pearlite structure is a great choice. It's from skyscraper beams to surgical scalpels. The ability to control steel's microstructure using phase diagrams and TTT curves is what makes modern engineering possible. It's all about controlling the heat and the time to cook up the perfect steel for the job. Thanks for watching. If you found this deep dive into metallurgy interesting, be sure to hit that like button and subscribe for more engineering content. See you in the next video.